in order to use the fundamental theorem for line integrals in general, we have to know that our vector field is actually the gradient vector field of some scalar potential function. And so very often that'll be the first thing that you'll want to do if you're faced with doing a line integral, is check your vector field to see if it is a gradient. And if it is a gradient, then we can use the fundamental theorem in this really nice way. So these next two activities just ask us to evaluate these line integrals by endeavoring to use the fundamental theorem of line integrals. And to do that, you should test these vector fields to see if they are gradients. And if they are gradients, find their scalar potential antiderivative, and then use the fundamental theorem to compute these two line integrals. So let's take a few minutes to work on this piece, and then after that, we're going to move forward into talking about what does this have to do with circulation, because circulation is the big question for us for the day today. So the first thing that you did wisely was to test to see whether this vector field could possibly be a gradient vector field of some scalar potential function. And for that, you used our screening test. That screening test is going to come back to haunt us and help us as we move into the next section of the text. So you took the y partial derivative of the x component and the x partial derivative of the y component, and in this particular example, both of those partial derivatives were equal to 0, and so in particular, they're equal to one another, right? Which is our screening test for whether something might be a gradient. And so since the screening test was passed, there is a chance for there to be a scalar potential function, and so then you went about trying to find it, right? By finding the x antiderivative of the x component and the y antiderivative of the y component and matching the two of those things up. You found out that x squared plus y squared, potentially plus a constant, if you like, but we can take that constant to be anything we like, is a scalar potential function for this vector field. And so according to the fundamental theorem, we then just have to evaluate that scalar potential function at the ending point, which is -1, 0, and at the starting point, which is 1, 2 of our path, subtract those results, and that gives us the value of the path integral of that vector field from that starting point to that ending point, regardless of how we got from starting point to ending point. So it didn't matter that this was a line segment. It could have been a portion of a circle, it could have been a spiral, it could have been a piece of a parabola. It doesn't matter what it is. As long as the starting point and ending point are the same, this integral is path independent.